This is continuing our review of integrals that we learned in Calculus AB before we start with the new techniques we're about to learn in BC. So first, the rule for natural log, or du over u. And you see there the rule. If you end up with du over u, then the rule is the natural log of the absolute value of u plus c. So a couple examples we'll see here be like this one, x over x squared plus 1. We're going to have to use u substitution. U is x squared plus 1. The derivative of that would be 2x dx, which isn't quite a match for what we have over here. That's x dx and 2x dx, so not quite a match. We do need to divide that 2 over. Now we have our match, x dx. So we'll have 1/2, I'll just pull that out front, and we'll do du over u. Now make sure if you see du over u, it's exactly du over u. If you see du over u squared or du over the square root of u, then you just bring that thing up and you add one to the exponent and divide by that number. It's only if it's du over u that you use the natural log rule. So we know this will become 1/2 times the natural log of the absolute value of u plus c. So that's 1/2 natural log of the absolute value of x squared plus 1 plus c. A couple things I'll point out just about this particular problem. Since it's x squared plus 1, that's always positive. There's no way to get a negative out of that anyway. You could drop the absolute value signs if you wanted and just put parentheses. There's nothing wrong with keeping them, but just know that they're not required since x squared plus 1 is always positive. Also, the properties of log allow you to move that 1/2 up as an exponent, meaning you could also write it as a square root, because this 1/2 can move up here as an exponent. That's not required, just letting you know those are all equivalent to each other. Okay, let's look at one with trig. When in doubt, if you're doing u substitution, choose u as your denominator. So I would say u equals tangent x, du equals secant squared x. And that's perfect, it's an exact match. I get du over u. I know the rule for that is natural log of the absolute value of u plus c. So we have natural log of the absolute value of tangent x plus c. So that's a really quick review with natural log. Next rule, integral of e to the u du. It's the easiest one there is. It's just e to the u plus c. So this example, actually before I do that, when it comes to problems with e, the general rule of thumb is that if there's just one e function in the problem, like there is here, then your u is going to be your exponent. If there are multiple e's, then you need to go with your normal rules about looking for things inside of a power, inside of a radical, a trig function, or in a denominator. But here there's just one e, so it makes sense to make u the exponent. Derivative of that is negative 2x. And we're going to have to be kind of creative because we've got to change a negative 2 into a positive 5. I'm going to do this in 2 steps. I know I don't want negative 2, so I'm going to divide that over. I do want a 5, so I'm going to multiply both sides by 5. Now if you're slick enough to figure out that you need to just multiply by negative 5/2 in the first place, that's awesome. Go for it. But it's always okay to just do it in 2 steps and make it clear for yourself if you need to. So this gives us negative 5/2 times the integral of e to the u du. And that rule is simple. It's just e to the u plus c. So we get negative 5/2 e to the negative x squared plus c. So anytime there's just one e, u is going to be the exponent. Next, we see one that has a bunch of e's in it. So this is the case I was talking about where you need to look at just the normal rules, something inside of a power, a radical, a trig function, or a denominator. So I would try out the denominator here first to see if that gives me something. Well, if I take the derivative of that, the derivative of e to the x is just itself, it's e to the x. The derivative of e to the negative x is negative e to the negative x. Because remember, it's itself times the derivative of the exponent. So the derivative of the exponent would be negative 1, so it just changes the sign in front. Well, that is a perfect match for the top. So we actually end up with du over u. Hey, that looks familiar. The rule for du over u turns into natural log absolute value of u plus c. So we get the natural log of the absolute value of e to the x plus e to the negative x plus c. So that kind of comboed the e to the x rule and the natural log rule all in one. Alright, now I didn't put all the rules up for this one because there's 3 of them. You should know them by now. That's the inverse trig rules. So this is one of the inverse trig. Just a reminder of a way that you can kind of know it's probably inverse trig. Anytime your biggest power on top, in this case is 0, there's no x's at all, and your biggest power on the bottom, in this case it's x squared, anytime they're different by more than just 1, it's probably an inverse trig problem. If you go back to this first example we did, if you notice on top it was x to the first, on the bottom it was x squared. They were just different by 1 power. So regular u sub worked just fine. For this example, our power on top is 0, and on the bottom we've got a squared. So that's not going to work out really well for us with regular u sub. So we have to use inverse trig. If you remember, there's really just 3 inverse trig rules. That's arcsine, arctangent, and arcsecant. The sines and the secants both have square roots. And the tangent has a plus, so that the t looks like a plus, so that's how you can remember that. Sine and secant both have square roots, so you know this has to be either arcsine or arcsecant. And since it has something in front of the square root, it is arcsecant. So the way I always approach this is I just wrote the rule right here. Okay, now we need to identify our a squared and our u squared. So a squared is 9, and our u squared is 4x squared. Keep in mind, even if on some other problems they reverse the order of what they write, a always has to be a constant, u always contains the variable, no matter what. A always is just a constant, u contains a variable. Alright, so back to what we were doing. U squared is 4x squared, so that makes u 2x, because you just take the square root of 4x squared, and then du would be 2dx. Now the reason I chose to do an arcsecant problem is it's the trickier one, because not only do you have to make your du match, you have to make the u match. Okay, well this says u should equal 2x, but if you look, we just have 1x. So we're going to have to adjust that and make it 1/2 u equals x. So I'm going to put a 1/2 out in front of my u. Same with du. It says du should equal 2dx, but we only have 1dx. So we'll make that 1/2 du equals dx. And we put a 1/2 in front of the du. However, if you notice, we get a 1/2 on the top and a 1/2 on the bottom. Since the 1/2s both canceled out, we actually don't have to adjust our overall coefficient at all. Now just so you know, that doesn't happen every time. You won't be able to cancel them both out. You may end up with a 1/3 over 1/2 or a 2 over a 5 or anything like that. When that happens, you've got to put it on the right side of the equation also, because whatever you do to one side, you've got to do the other. But it will often happen that it'll cancel out for you. So since everything lines up, we just plug in our a and our u. And we call it a day.